So welcome everyone. Before I go into what exactly Reframe is and how we use it at CSCS, I want to give you some idea what is the background that we had and why we use Reframe. So we do regression testing a lot at CSCS to guarantee quality of service. So it was very nice that we have just a precise talk, and he was talking about the difficulties they have to guarantee the quality of the performance of the software and the sanity of the software, right? Guarantee they're correct. So that's exactly the open source tool that we can provide not only to Precise, but to the entire community on how actually solve this problem. So at CSCS, because we invest a lot on guaranteeing quality of service of our computer services, we test every single computer every day. We test everything. So how we used to do that? We used to write this big shell script that would go into everything and test, seeing if the performance was being correct, if the numbers were being produced correctly, and it was really tough to maintain because we were doing a nice thing, but using a not very nice software methodology. So for that, we started to develop a better framework that's called Reframe that we can actually do the testing. Reframe is actually written in Python 3, and we try to make it easy for anyone to use it, from software developers to system administrations to any normal user who wants to just run our cluster and can test their software. So the way that we try to do that is basically abstracting away our computing systems or the internals of the computing systems. Some things that are difficult for some users to run in HPC systems because we do have modules, we have different MPIs, and the MPIs are highly customized for that computer node, that computing system. And when you change the cluster, you have to use another MPI because the other MPI is highly customizable for that one. So you have to be keeping track of all these things. So we try to simplify the usage of our regression testing, of how testing on Reframe by abstracting away these concepts. So that way, basically the person who is writing the checks, or if I want to write, for instance, a precise check, I don't need to think about it. I just have to think about the logics. What will my program will need as input, what will my program need as output, what I can read from output, and how can I measure the performance. So we have been developing Reframes internally CSCS since 2016. We went public, and now in 2019, we basically have 18 forks and 35 stargazers, right? Last week was 32. That's the reason why I said 32. It's a bit tough to count these things because it's all the time being updated because people are actually using it. And one of the reasons why people are using Reframe is because we have a very nice design goals. One of the design goals we have is productivity. So which means that whenever we have a user, we report the bug, and the user, this bug, we can test it later. What we do, we write a test. So it allows us, Reframe allows us to actually, on the fly, easily write tests. Because we do have systems from basic Linux box with Red Hat installed, CentOS installed, SLS installed, from highly customized Linux like Cray systems, we want our tests also to be portable. So we think a lot about portability. We don't want to write on test on one system and have to rewrite it to another system. One thing that I like about Reframe is that we have been running this daily in our systems, and we have never seen a stack trace of Python. Why? Because we are really robust. So we do a highly testing, not only of the systems, but also of Reframe. So we use Reframe to test Reframe. One of the key features of Reframe is actually, as I said before, the separation of the program environment and the system. Right? So you don't really have to care much about that. One thing that, for those who actually have experience with HPC, you always have to run jobs in HPC. You don't really log into the compute node. You do through a scheduler. So in general, they do what's called workload manager. So you can ask to say, I want 1,000 compute nodes, then you get 1,000 compute nodes, and then how you run your simulation there, you got a launcher, SRAM in our case, because it uses Slurm, and then you're going to run MPI calculations across this entire 1,000 machines, compute nodes. And some of these 1,000 compute nodes may be GPU enabled. We have a pretty big system with 5,300 GPUs. And the same system has 1,900 more or less CPU-only machines. So you actually, to run in one case, on the other case, you have to select what's called a partition. So you have to go to the GPU partition or non-GPU partition. So on Reframe, we also want to abstract out these concepts. We don't really want the users to be thinking about, hey, I have to be here, I have to be there, I have to run this way, this way. We just abstract out a lot of things. One of the concept that we have also in Reframe is we want to guarantee that we have a very complete documentation. So if you go to our website, you're going to see the reader docs, and you're going to be able to see our documentation start using it. So we're going to have tutorials. And on computer systems, on HPC systems, we have a lot of different people working on them. For instance, I work in the user support team, and I'm PhD in chemistry. I'm not a computer scientist. And how can I be developing, how can I be using Reframe? The reason we can do that is because we abstract out the people who are actually using Reframe from the people who are actually developing tests. We try to make easy for everyone who doesn't have a PhD in computer science, let's say, so someone who has is minimal knowledge of Bash to be using it. So we have two different APIs. One's called the front-end API. It's actually you call how to run Reframe, and we want it to be as simple as possible. So we have some flags, but if you want to run it, the minimum flag you have to do is minus R. And we like the green face guy, who's actually in general a user, wants to run Reframe, or a system administrator, but we also have a service at CSCS that you can run Reframe towards Jenkins. So you can have a robot running your code and taking Precise and checking the performance of Precise whenever you make a pull request, for instance. We also, for those who actually are developing Reframe tests, that's not so difficult also. So what you have to do is basically write a Python class and inherit from regression test. And decorate it with a small decorator called simple test. The simple test allows us to basically go through what's called a pipeline that I will show you later. And also enables you all the functionalities internal to the API, like the system abstraction and the environment abstraction. The environment abstraction is in HPC is not only about the variables that you have, but also about the modules system that you have. So some systems have Tmod, some systems have Lmod, Tmod4. If you don't know what I'm talking about, that is environment managers, module managers, where you can actually load different versions of software. And you don't have to care about it when you're running at CSCS, what's the type of modules you're using. One thing that we can say, okay, these guys are really doing abstracting, and so these things must be really difficult to use. In practice, it's not. The simple class that I'm talking about in general looks like that. So, okay, I'm clumping the lines because I have to fit into a slide. But as you can see, you just need to put like a descriptor. If you want to give a nice name, you have to have your class. Let me see if I can do this. So have your class. You basically init function inheriting from the regression test. You write a description name just to give you a nice description of what your test does. You say, I want to run on PITSDynth, which is this big cluster I told you with 5,300 GPUs, on the GPU part of the cluster. And then you can say, I want to test the GNU compiler, the Cray compiler, and the PGI compiler. I can say, the input file of my test is this .cu file, so it's going to be like a NVIDIA or CUDA source. So Reframe will identify that when you say single source, and we call the NVCC compiler. So he identifies the ending of your single sources and call the appropriate compiler. And we will be compiling these applications using basic flags, this -03, and you can give like executable options. On our systems, you need to know basically what's the module you have to load for CUDA, but you can do a mapping. You can always say, CUDA toolkit means this module use or module load that specific module. You can do mappings. And on this big cluster that I told you, we have just one GPU per node, so you can do the test with one GPU. But you can say here, like, If I am on system A, do 2 GPUs, I'm system B, do 4 GPUs. And so the way we do, by guaranteeing that we have a sanity check, guarantee if you have like the values are correct, we do this what's called sanity patterns, and you extract information from your test. So in this case, if the line time for single matrix is found in the std out, you're going to guarantee that it was passed, because actually it's the last line of your output. And then we can look at the output and it will say something like performance that was in gigaflops per second, and then if you look for this line, extract out this pattern, convert it to a float, and then we're going to be able to compare. So this number here, 50, is just a dummy number. So if this number is within 10% of this 50, we're going to pass performance. So as you can see, we're just trying to abstract away when all the logics are doing grep or getting the things comparing, converting to numbers into reframe. I can say that, yes, nice, these tests we can write, but do you really use it in, like, can I really use for my precise, can I really use for my scientific applications? Yes, so we have like an application at CSCS that's actually been developed every day, and they test it, and they use CMake in this case, and this is how complex it is for them to write a test. So they say, I need CMake, and I need this version of GCC because they were specific for this version, and I need to compile with these options. These compile options, my code. And voila, they get the code. Because we are using Python, and now we can use the amazing computer science concepts that we could not use in Shell. One of them is OO, so I can inherit. I can say, you know what, now I have my MPI version of the test, my MPI version of the test. To compile with MPI, I need this flag. So now I have two tests. I have the previous test, that was the basic one, that was only compiling with assert on. And I have now a second test that is basically doing the MPI version. And we can go on. We can actually not only a simple test on top, but we can also have this parameterized test. Then I have a factory. So instead of having actually to write a factory class or a factory function to spawn several tests, I can parameterize them. So in this case, we're parameterizing a different test that will compile for Haswell, Broadwell architecture, and a native architecture that can be the current one that you're using, can be any other architecture. Right? So you can see it's really simple to write tests on Reframe. And the pipeline that you get by adding these simple tests and this parameterized is a very fixed one. And this pipeline is more or less the following. You start the front end, you can say reframe minus R. What reframe you do, you go into a folder that you say, and then you look at all the Python files inside, import all of them that are reframe tests. And then it will start running, so you're going to pick a test, and you check, hey, is this test meant to be run on this system? If yes, we continue. If no, we just skip the test. And then the same applies to every single conditions that you can impose. We can say, is this test supports the program environment? So in my laptop, do I have a Cray compiler or not? If I say, no, I don't have a Cray compiler on my laptop, I'm going to skip the Cray test. I'm going to go continue to the GNU test that I have. I can go to the Clang test that I have on my laptop. And then this step we actually run on the machine that you actually have executed. On our supercomputing center, what we have is actually, we also have these compute nodes, right, that you spawn, you get to the scheduler, the execution. So we do all this analysis in a compute node, and you can run the test, on the local node, and we can run the test on the compute node. So we take your test, we verify it's valid, we set up the environment, so you clone, we guarantee that you running on a same environment that's always equal to the test that you have the environment that you have executed reframe. You compile your test if it's necessary, and we spawn these tests. Okay, my laptop does not have a workload manager, right? My laptop is just my laptop. I don't want to be installing things that I don't need. So one of the things that we don't need a workload manager, at least I don't need it. So what I do is basically on my laptop, I can say my workload manager is a local scheduler. So you actually just emit a batch script and runs on my local laptop. So this way, we can run from a laptop to Travis to our HPC systems. One thing that when we talk to the people from operations, they say, sysadmin means they say, the system is sane. For them, sane means the system is getting the correct numbers and getting the correct performance. On reframe nomenclature, we are a bit different. Sane for us means that we are actually giving the correct science, which means that I'm giving the correct number. And performance means that we're actually performing in that given range of value that we're expecting, that gigaflops of that time frame. So we do have different steps for checking the performance and checking the sanity. And after, if your test has passed or not, we clean up the stage and continue, and then report at the end. One way that you can do, or one type of test that you can do, is that you can compile only tests if you don't want to be running anything. If I want to compile a library, you can compile it. If you want to run only tests because you have already compiled, I don't know, an application in your computer, you can run it only. And you can, so we have helped the user, or we have already predefined places that you can do that. The way that you can actually define what's the paths that you have for your checks is -C command line, but you can also define different configuration files to actually define what is your laptop, what is this HPC center, and what is the other HPC center that you are running. So this configuration file allows us to map different systems and run the same test on different systems. So how does it look like when you run reframe? It looks like this. Basically, if you have passed all the tests, you just say run, okay, passed, run, okay, passed. So I can run Opray, I can run GNU, that example test, for instance. If something doesn't pass, what happens is that if you run, you say failed, and at the end you say the entire regression failed with one test case. And then you say report a failure. In this case, I just run one test, one check, so you only see one failure here. But you can see the reason why it was failing was performance. So it passed sanity. And the reason is because this number here is beyond the range that we have defined, the reference range, right? One of the nice things for HPC centers is that we care about the users a lot. And by caring about the users, we need to guarantee that whenever a user reports an error, we can identify the reason why. That means that we save a lot of logs. So at CS specifically, we have a centralized logging service that we save all syslogs. And reframe can also send to that syslog. So we can send all the performance of all applications that we are running daily at CSCS to this centralized and plot graphs. For instance, like as you can see, this is basically the logs of reframe execution of one application that's called Umber running the GPU, and this is the CPU version. You see a bit fluctuates. And then we can understand why, and we can report why it was smaller or why it was higher. Then we can understand. The usage that we have for reframe inside CSCS in our National Computer Center is basically we run through the three major clusters that we have, the PITSDYNE, PITSCache, and Leone. PITSDYNE is anyone can access to projects. PITSCache is the one that we do the climate calculations, so the simulations that say it's going to rain or not rain, they're done in our center. And the Leone is a private cluster for the customer. So there, on these three clusters, we run what's called production test that I told you that we run daily, maintenance test that we basically run before doing an upgrade in the system, and after doing an upgrade in the system, and what we call diagnostics. When a node goes bad, we run some tests to bring it back before. And why you do that? Because we have seen really nice things with reframe that allows us to probe and improve the quality of services. Sometimes before the upgrade, the application is running with a given performance. After the upgrade, the application drops performance or increases performance. So then we go investigate the reason why. And majority of the case, we can bring the performance up back to the original. And if we didn't have reframe to actually monitor that, the performance will be bad and we wouldn't notice. Only the user will be complaining. So the way we do that, we use Jenkins. So reframe is taken from Jenkins. And then we can see that the nice thing about Jenkins is that you have all these nice interfaces that we don't need to care about logging into the system. We can just look to the web browser. So we like it very much because it guarantees the quality of services of our systems and the application that we support. But we also want to empower users. So at CSCS we have a CI service. So you can apply for computer time at CSCS, apply for a CI service there, and then be running, let's give an example, Precise every day and test if it was performing and at a real supercomputing center. For that, we have actually integrated tested reframing integrations not only in our CI service, but also on public services like Travis, for instance. This way we allow you to be developing on your laptop, testing reframe on your local laptop, making the pull request to GitHub, working on Travis, the same test that you have written for your laptop, and bringing the same test to our computing center, so you're cross boundaries testing it. And internally we use Jenkins, so the usage is the same that we have for our own tests, right? So for us it's really nice because we can debug in the same interface. So this is how it looks like internally at CSCS, and as you know, this is how it looks like on Travis, right? So we can actually have a nice integration in all these cases. So just to conclude, I know I speak very fast, and I haven't spoken very fast, but just to summarize the take-home message about what Reframe. Reframe is a regression test framework that allows us to guarantee quality of our software, and it's written in Python 3. It can be portable across different computing systems, from your laptop to HPC systems, can be used in different HPC systems, and gives you a nice way to verify where you have failed, right? To get comprehensive reports. One thing that we are missing on Reframe is dependency of tests. So you can say test A depends on test B, which depends on test C. So it's on our future direction, our roadmap. And we have support to run any command line inside Reframe. But we only say that we support something if the usage of that thing is really simple. So today we do support containers at CSCS. We run container tests at CSCS, but we don't say we support containers because the usage is still too much commands. We are working on simplify the interface, so you can say this is my container, this is what I want to run, and run it to make everybody's life easy. And we have been asked by one computing center to have what's called benchmarking mode, so we can stress the system and get different reports only. But this is very specific to supercomputing, where you want to kill a machine, want to see the limits. So we have some partners that have been using Reframe, as you can see, and the majority of them are supercomputing centers, but we have some companies involved. And if you're using Reframe and you haven't told us, please tell us, because we have many people using it and we didn't know. So I want to acknowledge the team that has been developing Reframe internally at CSCS. As you can see, we have a lot of people. So because Reframe and regression testing is very important for us. So this is a project that is not going to go away in the near future, for sure. Because HPC centers, they do require regression testing. With that, I want to thank you for your attention, and any questions?
Any questions for Victor?
Yeah.
So you, as I understand, you can only run tests written in Python. You can execute it, you cannot, but do you have a way, like if the user writes a script, like you just say, okay, just test the script and then you different something?
Yeah, so the question was, if I understood, you can only write tests in Python. Actually, no. I mean, this test is written actually in, the test itself in Reframe is written in Python, but this application is an NVIDIA application, right? So you can say, I want to run this script, just put the script there, and you're going to run the script.
But you still have to write this for Python?
Yeah, you still have to wrap this interface, yes.
Because I mean, what I feel like, so this adds quite some complexity, at least from a basic user, and then it makes the thing create new tests harder. And the other thing also, I'm just afraid that what you're going to test is not exactly what the user is going to test, because you do something in the back end, you might create some environment variable, you run some module, and the user at the end has something a little bit different.
So the comment was basically that by adding this step of writing the class, you may add some complexity, right? Because you just had your shell script before, and now you don't have it. Yeah, this is true. In the beginning of Reframe, by 2016, we shared the Reframe a bit with operations, and they said, dude, this is very difficult to use. This is like, you have to have a PhD in computer science to use it, because it was very difficult to use. So we are slowly incrementally the interface to make it as easy as possible, right? So we have some internal ideas that I don't know if I can share about simplifying this and using different input methods, but it's not there yet. It's in our roadmap, but it's not in the near future roadmap. So yes, today you still have to do some Python to have it. Yeah, you have this layer, Python layer. Yeah, yeah. So just one comment from Vasilis, the lead developer of Reframe.
So yeah, I mean, as you said, it seems like an extra complexity to write Python class around your test. But if you just have a single type of system to test, then that's fine. Go for a shell script. But imagine you have to test on different HPC systems, then the complexity really becomes much higher, and you want to abstract this away. For example, you don't want to have in your script the logic of did my job finish? When did they finish? We have examples of people developing software, and they have ended up writing thousands of lines of bash script just doing stuff that we're handling by the framework, and they could do the same stuff with 20 lines of Python code, because we have separated the system part versus the logic of the test. That's the key advantage. Yes, I agree, you have to learn a bit of Python, write something, but in the longer term, and depending on what you want to do, then it can really untie your hands.
Any other questions? No? Thank you very much.
Thank you, Victor.